Hi, my name is Mike Sullivan, and I'd like to introduce you to some exciting research we've conducted at NVIDIA into a no-overhead security mechanism called implicit memory tagging. The problem that we address is that of memory safety. A memory-safe program guarantees that memory objects are only accessed between their intended bounds and during their intended lifetimes. Unfortunately, many very popular programming languages, such as C or C++ and CUDA or OpenACC, do not ensure memory safety, potentially allowing memory safety violations to occur. A memory safety violation can either violate the intended spatial memory bounds, for example through a buffer overflow, or temporal memory bounds through a so-called use after free. This threatens both the correctness and the security of a program, and it is a major source of both bugs and security vulnerabilities. Memory safety violations are important. They can be conducted remotely without any physical access or exotic techniques. Several large companies have reported that memory safety violations are the most common class of exploits. One example is shown here, using data from Microsoft's Common Vulnerabilities and Exposures database. You can see that roughly 70% of vulnerabilities have to do with memory safety. Because of its importance, many prior techniques have attempted to ensure memory safety for unsafe programming languages through architectural changes. One of the most popular techniques is called memory tagging, which is a mostly hardware scheme that is also the focus of this work. Memory tagging proceeds as follows. First, the software runtime uses special instructions to associate a key tag for each program pointer and a lock tag with each entry in memory. The key tag is typically inserted into the unused bits at the top of a pointer's virtual address, thus requiring no dedicated storage. However, the lock tag is associated with each entry in physical memory, and thus it may incur storage overheads in existing implementations. At runtime, the hardware detects and reports a fatal memory safety violation if the key tag of a pointer mismatches the lock tag of the memory that pointer accesses. Thus, the movement of the lock tag potentially incurs some performance overheads in existing implementations. Ultimately, memory tagging has both benefits and drawbacks. The benefits of memory tagging include its simplicity, efficacy against both adjacent and non-adjacent buffer overflows, and the fact that it is employed in some current products. The main drawbacks of memory tagging, however, have to do with the expense of lock tag storage and movement. Limited size tags can be used to reduce storage and performance overheads, but this comes with lowered probabilistic security guarantees against non-adjacent buffer overflows. This leads to an unfortunate trade-off between cost and security. Memory tagging storage overheads are especially painful and costly on GPUs, which offer a relatively small main memory that cannot be increased by the user. Also, the performance overheads of memory tagging are especially costly for emerging GPU workloads with fine-grained access patterns. For this and other reasons, our paper primarily focuses on providing no overhead memory tagging on GPUs. Broadly speaking, there are two implementation alternatives in current use. The first, which I'd call the tag carve-out, embeds the tag metadata in shadow memory that is stored in a dedicated carve-out. The second uses dedicated sideband redundancy to store tags. Since ECC is metadata that is normally stored in sideband redundancy, one option is to steal away ECC checkbits to store the memory safety tags. These organizations are also called disjoint and widened tag storage in prior work. Both the tag carve-out and ECC stealing implementations have benefits and drawbacks. The tag carve-out puts fewer constraints on the underlying memory system, but it comes with tag storage overheads and performance overheads due to tag movement. Meanwhile, ECC stealing comes with no storage overheads or performance overheads, assuming some existing redundancy is taken away from the error-correcting code. However, this obviously has a reliability drawback, as ECC bits are normally there for a purpose. In our paper, we explore the costs of both existing tagging implementations. This slide shows the performance overheads of the tag carve-out on a compute class GPU using cycle-accurate simulation. 3 benchmark suites are shown: MLPerf training, mixed HPC and sparse linear algebra workloads, including some graph analytics, and the stream microbenchmark. Now, one could stare at this plot for a while, but in the interest of time, I'll just point out two things. First, the average performance overheads are modest but non-zero. On average, there is roughly a 1 to 4% slowdown depending on the benchmark suite. However, some programs suffer from a much higher overhead, up to 30 to 40% depending on the tag size. These are programs that feature both high DRAM traffic as well as poor locality. ECC stealing avoids these storage and performance concerns, but it comes at the cost of greatly degraded reliability and availability. Each single bit of redundancy stolen from ECC results in roughly a 2 times increase in the silent data corruption rate. And if too many bits are stolen, we may even sacrifice the ability to correct errors, which can violate the availability requirements of large-scale systems. Smaller tags can of course be used to limit the overheads of memory tagging, but unfortunately this also limits the security of the approach. The detection rate of memory tagging is proportional to the total number of tags that we can draw from. Thus, if we have a small 4-bit tag, this limits the detection rate to less than or equal to 15/16. Next, I will show how implicit memory tagging avoids the overheads of current memory tagging implementations while simultaneously improving security by orders of magnitude. Implicit memory tagging leverages the existing system ECC to check for memory tag mismatches, thus providing no overhead memory safety. The enabling technology behind implicit memory tagging is something we call Alias-Free Tagged ECC, which is a general mechanism for performing tag equivalence checking with large tags using the ECC check bits themselves. Alias-Free Tagged ECC is based off of the observation that the ECC codes used for computer memories are shortened. This means that they could theoretically protect more data than we require them to. For instance, consider a 10-bit secdead ECC code that can correct a single bit and detect all double-bit errors. Using 10 bits, we could theoretically provide error correction for up to 501 data bits, but the GPU memory access size is smaller at 256 bits. Alias-Free Tagged ECC uses the unused error correction capabilities to check for the equivalence of a tag. It requires a minor yet careful redesign of the ECC code. Ultimately, Alias-Free Tagged ECC has the following nice properties. First, Alias-Free Tagged ECC can unambiguously detect and attribute tag mismatches in the absence of a data error, meaning that there is no risk of missed tag mismatches. It maintains the error correction capabilities of the code as well, and also has no impact on the data error detection capabilities, so long as tag mismatches are considered fatal. Finally, Alias-Free Tagged ECC is designed to embed the maximum width tag with these properties. We characterize the maximum tag size in our paper, and for most common code word sizes, a tag size of 1 less than the total ECC redundancy is possible. I know that the gory details of ECC design are not everybody's cup of tea, but for anybody who is interested, the paper gives a principled construction to create alias-free tagged ECC codes. The main idea of implicit memory tagging is simple, and I hope obvious by this point. It applies alias-free tagged ECC to tag memory for memory safety purposes. Let's step through an example of implicit memory tagging in action. Let's say that we want to write a piece of data to memory. The implicit memory tagging ECC encoder takes the written data and the already verified lock tag as inputs. It generates the ECC check bits using both tag and data, writing the result to memory. Crucially, the lock tag itself is never explicitly stored in memory. Rather, it is embedded in the ECC check bits, requiring no additional storage. When it comes time to read that memory location, we know the key tag associated with the pointer that is reading the memory. It is passed to the implicit memory tagging ECC decoder, along with the data and ECC check bits that come from memory. The implicit memory tagging ECC decoder itself is the one to check for the equivalence between the key tag and the lock tag. Whereas a regular ECC decoder has only 2 outputs, one for the corrected data and the other to indicate that an uncorrectable error has occurred, our implicit memory tagging decoder introduces a 3rd output, which indicates that a tag mismatch has occurred. Implicit memory tagging has substantive advantages over the current implementations of ECC stealing or the tag carve-out. To demonstrate this, I will step through several options on the following slides. This slide shows the baseline ECC stealing and tag carve-out approaches, which are based on industry implementations of memory tagging. A 4-bit tag is associated with each granule of memory. The tag carve-out requires 3% additional storage, and it suffers from up to a 30% slowdown. ECC stealing, on the other hand, has no storage or performance overheads, but has almost a 16 times higher silent data corruption risk due to the degraded ECC capabilities. Finally, both approaches have relatively weak probabilistic security because of their limited size 4-bit tags. The exact security depends on the details of the memory allocator used, but in any case there is a significant chance for missed memory safety violations. Next, we show two implicit memory tagging organizations. The one on the left uses the minimum amount of redundancy possible for sec-dead protection, while the one on the right uses the full redundancy that is provisioned by GPU DRAM. In either case, implicit memory tagging avoids the overheads associated with the baseline approaches. And due to the support for larger tags, 9 bits or 15 bits in this case, implicit memory tagging simultaneously improves the security by 2 to 3 orders of magnitude. Finally, we can also consider same security configurations of ECC stealing and the tag carve-out, which increase tag sizes to match those of implicit memory tagging. This matches the security of implicit memory tagging, but it comes with even more severe overheads, making these organizations highly impractical. In summary, memory safety is an important concern for many very prevalent programming languages. We dove into a popular fix for this problem called memory tagging, which is an attractive mechanism, but it suffers from overheads and limited security in current implementations. We then describe implicit memory tagging, which relies on a novel class of ECC codes called Alias-Free Tagged ECC to perform memory tagging. Ultimately, our results show that implicit memory tagging works with no storage overheads, no performance overheads, and without affecting the error correction and detection capabilities of the underlying ECC. It also makes large tags practical, improving the overall system security by orders of magnitude. This concludes my talk. Thank you very much for your time.